So in the previous video, we got an idea of what the heck a z-score was and how to calculate it. So we know how to use the calculation, we understand what it is. Those are two questions I could definitely ask on the exam. Now, once we calculated z-scores, there are normally two things that I will then write the question about. And one is trying to figure out if something is unusual or comparing two things. So the first thing is we could use our z-scores to identify whether or not something is an outlier. This should only be done in the case of pretty symmetric data, because remember, our mean and our standard deviation are not robust to outliers or skew, and therefore our z-score would not make much sense in a case of a skewed distribution. We should be using that fence formula we did for the box plots. But if we have nice symmetric data that is approximately normal, which means it follows that bell curve with symmetry, then we can go ahead and use a z-score to see if something is unusual. Typically, a z-score of 3 or more is considered unusual, but other commonly used cutoffs are 1.5, 2, and 2.5. It's very arbitrary here. It's not as set in stone as that 1.5 criterion for the fences. So people will use different things here. I know that when I was working at UCSD, one of the things I did was I looked at blood glucose measurements, which is where I got the example for this next exercise. And we had people whose blood glucose measurements were z-scores of 4 and more because they were just so crazy unusual. And so we would do research with them, both included and excluded, depending on that 4 or 3, however many. So anyways, let's look at evaluating outliers using our z-scores. So first example, or only example here, is exercise 2.7.1. Blood glucose levels are normally distributed. So this is what's telling me that the mean and standard deviation are legit. I can go ahead and use them if I really wanted to. I could draw a cute little normal curve, my bell-shaped curve, with a mean. Okay, so we got our mu of 85 and a standard deviation of 5, so our sigma. Now, technically, these could be an X bar and an S, depending on whether this is sample data or population data, but there's nothing here to tell me that these were from a sample, so we're going to use mu and sigma. Generally speaking, whenever I say normally distributed, I'm sort of then saying these are the real values. Use them. They're gospel. The next question says, or the actual question says, would a patient with a blood glucose level of 68 be considered unusual? All right. Well, this is a good hint that we should be using the z-score formula, because we know z-scores can help us see how far above or below average someone is. So if we use our z-score formula, x minus mu all over sigma, we know that our actual level here is a 68, so much less than average. We have our mean of 85 and our standard deviation of 5. So I like to do this. I'm going to do this in my 2 steps, and this is just to sort of show you what the heck we're doing again with our z-score. So we found out that this 68 is 17 points below average, but we don't really know if that's unusual or not unless we look at the standard deviation, because 17 points difference on an SAT score is nothing, whereas 17 points difference on an ACT score is basically the whole freaking score. So it really matters what our scale is. So our scale is 5. So if we take that and do our division, we get negative 3.4. So based on this, and based on this idea of everything should be within 3 standard deviations of the mean, in fact, if we look back to the standard deviation section, for normally distributed data, 99% of our data is going to be within 3 standard deviations. So the fact that this is outside of that 3, if I were to do my little empirical rule drawing, we had this 85, and we would subtract off 5 to 80, then to 75, and then to 70, right? We only do the 3 little bunny hops in the empirical rule, and this person was at 68, right beyond that 70. So they are over 3 bunny hops away. They are very unusual. So 68 would definitely be considered unusual. I'm going to go ahead and just write a little sentence, unusual, because it is more than, I know my handwriting is terrible, 3 standard deviations, I'm being lazy, below average. I know this one then asks us for 98. 98, again, you would just do the same formula. The only thing you would change is throw this into a 98 instead. If you do that, oops, that is so not right. Typing random things in my calculator. You end up, for 98, you get a z-score of 2.6. And this is a questionable one, right? Based on the 2.5 criterion, this would be unusual. It's still pretty far out there. So I would still say this is pretty unusual. It is not an outlier by the 3 criterion, but it'd be an outlier by many, many people's criterions. So like I said, a little arbitrary at the moment. Oh goodness, I didn't mean to erase that. But that's the best we have. So if I'm on a test, I don't normally ask you this question, and if I did, I would give you a cutoff. I would say based on using a 2.5 z-score criterion, or a 2 or a 3 as being considered unusual, anything beyond that would be our issue. The other way we can use z-scores is to compare apples and oranges, like I mentioned, the ACT versus SAT idea. So I have this silly example here. Your friend is also taking stats, and they score an 87 on the first exam, while you scored an 83. So right now it looks like your friend is a better statistician than you are. But you argue his exam was easier. The class average was an 80 with a standard deviation of 5. So let's just go ahead and start thinking about this. We got friend, we have you. We know the friend actually scored an 87. You scored an 83. So right now, friend looks better than you. But we dive into it. His class was easier. The average on his exam was an 80 with a standard deviation of 5. Well, your class had an average of 70 with a standard deviation of 10. All right, using z-scores, who did better relative on the test? So this one we know is a better question. Doesn't talk about unusual, talks about better. Like I said, there are 2 questions I could be asking. And the only way to figure out this better relative to the rest of your classes is to use z-scores. We could obviously, and even on the tests, when I have this question, I usually say you can use z-scores or give me a drawing or diagram. So if you don't feel comfortable with the z-scores, but you feel real comfortable with the empirical rule, you could actually just do this and say, okay, well, the friends was an 80, then the next one was an 85, 90, 95. Whereas in your class, 70, 80, 90, and 100. And you kind of just look at this and say, okay, well, you were an 83, and your friends was an 87. That's probably bad. So it's a little hard to see still, but you could use this drawing to sort of go, okay, well, we're both a little over 1 standard deviation above. But like I said, if we just want a numeric value for this, we'll use our z-scores. X minus mu, so X is always the observation. How unusual is this 87? Well, it's all relative. How far above the mean is it? And how many bunny hops? How many standard deviations is that? I can't do this math in my brain. 1.4. So your friend is 1.4 standard deviations above average, while you are in 83, but from a much lower mean. But there's a hell of a lot more spread in your guys' class, according to this made-up numbers. So here we get a 1.3. So hard to see based on my drawings. I obviously drew this 7 really far over. But based on this, your friend did better relative to the class because they were further above average. So usually if this question's on test, it's sort of like 5 points. And usually there are points for getting the 2 z-scores correct, and then points for making the correct decision based on those z-scores.